Here is meant to document a little bit of the snags that I hit while going through the solutions in chapter 3 of Peskin and Schroder. So I'm not going through the whole solutions, I'm not going through every single problem, because there are detailed solutions out there on the web. So what I've done is I've gone through the solutions on the web, and I will link it down below. And to the parts where it needs more proof or needs more explanation that I found gave me a little bit of problems, I'm gonna explain it here, and hopefully it will save you some time, because it's what I would have liked when I was going through chapter 3. Here is my walkthrough of the solution of Peskin and Schroder's problem 3.1, which are the representations of the Lorentz group. In the question posed, the notation is used as J to represent the Lorentz group. I'll be using a more widely used notation, which is the mathcal M. So in other words, our expression will look like this compared to this in Peskin and Schroder, and our rotations and boosts take this form. So with that, we can continue with the question. So as in the question right here, we have to prove relations of these form before we can go on to prove the more complicated J plus and J minus ones. So we'll start off with the relation between the rotations. Which takes this form, and we'll have to do it by manipulating these epsilon functions. So we can first expand the left hand side. And this will take a general form of IKL instead of IJK, because there's a J used right here. And in our notation we use M instead of J. And same for here. And instead of using JKI, cycling the IJK indices, we will be using JMN. So we don't repeat the indices on these two terms. Like that. So here we can factorize out our epsilon functions, and we are left with a familiar object which is given in the question and in the book itself, which is the commutator of the Lorentz group. Expand the previous line, we get the full expression for the commutator of the Lorentz group with the imaginary number factor. And what we can do here is take the metric and use it to modify our epsilons. So in that case, it will look something like here. L changes to M, so you can change either the L here to an M or the M here to an L. And I'm just going to change the M to an L. So that's how the first factor would look like now. And we also need to add in a negative sign, because we're dealing with spatial indices here. That's why the negative comes out in our mostly minus metric. You can do the rest you can do similarly for the rest of the expression, which I'm not going to write out fully. So at this point, you should have a bunch of epsilons that are paired together like that, and these epsilons should share one common indice or index, if that's how you say the singular. And you can use the identity here, and you can use this identity here to replace all the epsilons in the expressions to a bunch of delta symbols, which now I will bring this whole down and I'll work out the rest of the expression for you. Now if you work it out, this should be the full expression with all the delta symbols. And what the delta symbols can do is they can directly modify the indices in the M. So you can see, for example, the first term. has a negative delta in and kj. So the k can turn into a j, and the n can turn into an I. So that's what we can do. And for this second one, we should get the I and j don't affect anything in the m because there's no I and j here. But what this does is this should be a k. So there's a k and n. So what that does is it turns this m into mkk or m and n, whichever you choose. So it has two of the same indices here. And if you know the representation of the Lorentz group, if the indices are the same, because it's just the anti-commutator of a bunch of derivatives, the commutator of a bunch of derivatives, then this should vanish. So all the m's with the same indices on top should all vanish. So in this case, a term like here lm and here lm, so this will turn into an ll or an mm. So this one vanishes, just like this one. And this one has an ln, you have an ln here. So this one changes to an mll or an mnn. So this one also vanishes. And you can do the same for here, km, and there's a km here. You can vanish this. So what you should get is a bunch of mij's left because of all the remaining non-vanishing delta symbols, which I'll write out now. So now if you work it all out, you should get 4 negative mji's, and since there's a factor of a quarter here, it should just cancel out to give you negative I mji. And if you want to flip the indices of ji to ij, you actually change this to a plus sign, and this becomes ij. That's how our expression looks like. But it doesn't look like the desired expression just yet, because we need to convert it to the lk generator of rotations. So how we'll do that is we'll split up this mji into an equivalent form, and then we'll manipulate the algebra a bit more. In the previous board, you need to show that the left hand side, which we have now shown equals to ij, is equal to the right hand side, which takes this form. So what we'll do is we'll split up this mij a little bit more. So what I've done here is I've just doubled the number of mij's and divided it by half to maintain the equality. And what we'll do is similar to what we did a few steps ago. So you're going to change mij into mji, and for that you need to so now it should look like mji. So this is still equivalent. And now we can do a little bit of manipulation of the algebra, and we can take back out the delta symbols that we multiply into the m's of this form, which is basically, for example, this delta il, we change the l here to an I, and jm, we change the m here to j. Similarly, if you change the l here to j, you get j, and then m to I, you get I. So you get back mij minus mji. So that's what it looks like. And here, using the same identity that we had before, we'll find that this bracketed part is equal to the multiplication of 2 epsilons that share one common indice. Like this. And finally, you can take the half here, so you leave out the I, you take the half here, and you take this second epsilon, and you take this Lorentz group to create a term of the form of this form in the bracket, and this is equal to lk, and you get your final right hand side, and so you prove the commutator. So in the question itself, the equation given for the Majorana formula looks like this, and I spent so much time wondering what this was because I thought it was the square, so I took it to mean this expression, which is the square of the, I guess you can say, the 4D version of the polyspin matrices, which didn't really work out given I was trying to prove a bunch of stuff that the question wanted you to prove, and you simply can't prove it if you interpret the sigma with the superscript 2 to be equal to that. So after quite a long while of trying and failing, I realized that this was not actually what the question meant. And then I thought, well, maybe it's the square of the 3D version. So I thought it was something like this. So I thought it looked something like that instead of the 4 version. But it also didn't work. So it turns out it wasn't there. And in fact, what it is the second of the polymatrices, which is the y-axis version, which turns out to look like this. Is it clear? Is it clear on the camera? Let's see if I can get it clearer. So it looks like this. So with this, it makes so much more sense, because if you get the complex conjugate of this value of the y polymatrix, then you'll find out that it's equal to the negative. And it works similarly if you do something like the conjugate, then you'll find that it's invariant to the Hermitian conjugate. So that's a little comment that I needed to make in case you're getting stuck on this also. Peskin and Schroder doesn't use a bracket around the 2 superscript. So I personally like to do it to differentiate it from the square to prevent confusion. So yeah, that's something I'll take note of. What about the West-Zumino model? There's an identity given in the solutions which says you can prove by yourself. And I didn't find it too difficult to prove, but here it is in case you need it. So we're not going to write down the full identity because it's quite long. So I'm going to deconstruct a part of it first, a third of the identity, which is one of the terms. And then we can later cycle the indices, and then you can prove the full identity itself. So we're going to work out one piece of the identity first, which looks like that. And we are really just going to do it the way that the answer key suggests, which is brute force. So we're going to expand out everything in the form of their matrices. So that's how it looked like, fully expanded out. And you just multiply everything out, and you should get something of the form which I'll write now. Now you can note that this final expression is just a bunch of numbers put together, numbers multiplied together. So these chi fields can actually be interchanged without any consequence, without imposing any kind of anti-commutation law or commutation law, because these are just components of the fields, which are just numbers. So you can completely just commute them and you'll be fine. And what you do with this is you sub in the respective symbols of the RST, the respective subscripts, and you can prove this super long identity itself by just making sure that all of these terms cancel out with some other terms somewhere and they were equal to 0. So that's the full proof of the identity. Yeah, and that's about it for this chapter. It's not too difficult. Most of it is just a lot of brute force and a lot of calculation. There's another comment that I can make on the last problem, which is on the bound states. You can see this problem right here, bound states, but I won't reiterate the points because it's been made by someone else, and I'll link their video down below. And that's about it for chapter 3. And yeah, if you need any more help, you can put it in the comments and maybe I can help answer if I can. Yeah, thanks for watching.